All right, good afternoon, everybody. Let's get started. So welcome to 6004. Before we dive into today's lecture, just a couple of reminders. First of all, in case you're not aware of this, tomorrow is a student holiday, so there's no recitation. This is due to the career fair. Lab 1 is due today, and if you have not done the check-off meeting, so if you submitted it earlier, but you didn't go to the lab to do a check-off meeting, I really encourage you to sign up for one of the slots. There's a post on Piazza detailing the instructions. You just basically fill out a doodle poll, and that way you don't have to wait or queue yourself. So you have a slot, you can just go in, do the check-off meeting, and that's it. Okay, so today we're actually shifting gears in 004, as you might have inferred from the title. So we're done with Module 1 with assembly language, and we're moving to Module 2, digital design. Right, so in the last few lectures, we have seen how the language of the computer is, and then how programs from high-level languages are translated into these sequences of assembly instructions, how data is structured in memory and in registers and so on, how control flow changes across multiple procedures, how to organize code in a way that's composable so that you get reusable procedures that can call each other, and so on. And so, there's a lot of things that you can do with assembly language already, right? You might not realize this, but you can talk to the computer directly. This is the actual interface that the hardware is implementing. You can build tools that emit assembly. So you can do things like a simple compiler, and this might seem quite complicated. Simple compilers are not that complicated, as you will see if you take, for example, the compilers course. But something that might arise more frequently in your professional life is you'll be able to actually debug tools that are wrong. So if the compiler sometimes does something that you didn't expect, you can actually go and look at the assembly, look at the output of the program, and figure out, that instruction shouldn't be there. And so this is quite useful. But at the same time, you're probably wondering why assembly is like it is, right? You probably have a lot of questions, like, why is there a register file and a memory? Why don't we just have a big memory? Why do we have instructions to move data between this register file and the memory? Why don't we just let all the instructions access memory or the register file, whatever they want? Why do we have the set of operations that are being implemented, right? Why, addition and shifts and logical operations? What happens if we add more? Why don't we have multiply, for example? Could we just add a multiply instruction? What happens if we do? What happens if we take out an instruction? Right? Are we suddenly able to solve fewer problems than we were able to solve before? And even more basic questions like, how long do these instructions take? Right? Are all instructions equally expensive? Do some instructions take much longer than others? And so to understand all of these trade-offs, really we have to take a deep dive into digital design and really understand how hardware is implemented. And look a little bit at physics, right? Go down to transistors and to gates and to the basics of digital design to understand all the trade-offs and really figure out why assembly is like it is. And in the process, you're going to learn not only how to design a general purpose processor, but also how to design hardware in general. And, in past years, students sort of have two reactions to this. Some students say, great, I finally will understand the whole stack. And some students are like, I like abstraction. All I want to do is write JavaScript. Leave me alone. So let me spend a couple of minutes telling you why, beyond intellectual curiosity, right, beyond just understanding how systems work, there are some really good reasons for you to deeply understand hardware. The first requirement, or the first, good outcome of learning how hardware works, is that designing cutting-edge systems requires intimate knowledge of hardware. And by cutting-edge systems, I mean systems that push the envelope of what is possible. And that's where most value is, and therefore, it is likely that in your professional life, you'll end up working, with things like a large supercomputer, a large cluster of machines, or a tiny embedded device that has to consume very, very little power and do a significant amount of computation with that little power. And that you can get much more mileage out of your tools if you know how your tools work. So that's one thing. But even then, you might say, yeah, but general purpose processors have a very nice interface, and you just tell me the code model, like I only need to know how expensive each instruction is, how many instructions can I do per second, and I'll be able to write low-level code for it. And 10 years ago, you'd be completely right. And in fact, to look deeper into why it is becoming more and more important to learn how hardware works, you have to look at how the performance of general purpose processors has changed over time. And that's what this graph shows. So this graph compares the performance of different processors built at different dates. So time is in the x-axis, and performance over some design from the mid-70s is in the y-axis. And note that performance is in log scale. Right? This is logarithmic scale. So whenever you see a slope, that's an exponential. Performance has been increasing exponentially over time. And in the 80s and 90s and up to the mid-2000s, you see that the rate of improvement is about 2x over 2 years. Every 2 years, you basically could buy a new computer system that would be twice as fast. Unfortunately, we cannot build chips we cannot keep any exponential going on forever. And so chip fabrication technology is reaching its limits. Current transistors have around 100 atoms. And you can't go much smaller than that. Or they're around 100 atoms wide. And so we'll see all these details later. I don't want to go into the details of why the slope has fallen. But the end result is that general purpose processors are not improving as fast as they used to. And as a result, custom hardware or specialized hardware is becoming much more prevalent. And so now you have many companies that are traditionally considered software companies that are building hardware. So Google is building hardware, Tesla is building hardware, Facebook is hiring a bunch of hardware engineers, same thing for Amazon. Apple has a bunch of hardware engineers and constantly asks us, why can't we get enough hardware designers from MIT? And so on. So it's not just a couple of chip manufacturing companies anymore that are designing these chips. And even if you say, I never want to design hardware in my life, you're very likely in your professional life to at least use some of these specialized devices. And these are not as well abstracted as general purpose processors. So they're doing things that are kind of weird, and they're doing it because there are good physical reasons, right? Because of physics, they're doing things in a sort of unconventional way. So learning hardware deeply will help you understand all of these devices, even though in this course we're going to focus on general purpose processors. Okay, so with that, let's jump into today's topic, which is the digital abstraction. So our ultimate goal is to build systems that process and store information, and that do so both reliably and cheaply. Right? We want to build really cheap systems, as inexpensive as possible, that don't break, or that where the signal or the data doesn't degrade over time. And so broadly, there are two classes of systems. First, we have analog systems that essentially represent and process information using continuous signals. So for example, this can be in general voltage, current, temperature, pressure, some physical quantity. And in this course, we're going to use voltages because guess what? Voltages are extremely efficient to generate and transform with electronic devices. And so you could represent information as a continuous voltage, right? As a continuous voltage waveform that changes over time, right? Now, this is a very natural way of doing things, right? Because the world is analog. We are actually, we have the ability to encode information directly as a continuous physical quantity. On the other hand, we have digital devices. And digital systems and digital devices represent information as a discrete collection of symbols, right? As a finite number of discrete symbols. Typically, these are bits, and so we're going to look at binary digital logic Some other technologies might allow you to have 3, 4 levels, but we're not going to get into those more esoteric technologies here. And the key insight here is that we want to design these digital devices, but in the end, the world is analog, and so we need to encode these digital symbols or these discrete symbols into a continuous signal in the end, right? So we're going to encode these digital values using ranges of a continuous physical quantity. For example, we can choose a range of voltage levels to represent a 0, right? And a range of voltage levels to represent a 1. And now we can encode information as a waveform that goes through these ranges, right? So this waveform would be encoding 0, 1, 0. Now, this is kind of unnatural, again, because the world is analog. But digital systems have one key advantage. So if there's one thing that you have to remember from this lecture, is that the key advantage of digital systems over analog systems is that digital systems tolerate noise. The whole reason we go through this rigmarole of encoding symbols into ranges of continuous variables or continuous signals is so that we can build systems very cheaply, and those systems are very reliable. If the waveform here changes a little bit because there's some noise, right? That will still be a 1. So now what we're going to do is, throughout the rest of this lecture, most of this lecture, we'll go through how do we actually derive an encoding that is robust against noise. This is not as simple as you might think. There's a couple of issues that we need to solve. But before that, let's actually take a little bit more of a deeper look at the issues with analog systems. So one simple example that you might have at home, or you might at least have seen somewhere, is an analog audio equalizer. Right, so an equalizer essentially takes a signal as encoded as a voltage, right, that represents sound pressure. This is ultimately encoding sound. And then it has different knobs here, and those are controlling gains of different frequencies. So essentially, this equalizer divides the signal into different frequency bands and then applies a different gain or a different amplification factor to each of the bands of frequencies. Then it mixes things back together, and what you should get is a frequency equalized voltage signal. Some processed audio signal where, let's say the bass has been amplified, or the mid-range frequencies have been amplified, right? Depending on how you want to listen to particular kinds of music, for example. So if you look into the implementation, this will typically be designed as a filter bank. So you have a low-pass filter, a band-pass filter, a high-pass filter. These are just RC circuits, and then you have different analog amplifiers with controllable gain that you set through these knobs. Finally, you put all these different signals together, and you get this output. But actually, the question that I have for you is: do you get what you expect? Is the output actually exactly this frequency equalized voltage input signal, given the gains that we have as inputs? Anyone? This is one of these love headlines. If I'm asking this kind of question, what is the answer going to be? Exactly. So it's not the case. But why? Right? Why don't I get exactly the output that I expect? What could possibly go wrong here? Yes?
Because there's noise you have to take into account.
Exactly. There is noise. There are 20 different types of noise, and they're all conspiring to slightly change the value of the signal. That's one thing, but there are others. There are other issues. So these physical devices, they're not all exactly the same. Ideally, we'd like all these amplifiers to have the same gain. In practice, there's going to be manufacturing variations. Not everything is going to be amplified the same way. And even if we produce these wonderful, resistors and capacitors, time happens, and so over time, these different components are going to degrade. The transistors or whatever active components within these amplifiers are going to change their behavior just because, that's how physics works. And so for these and other reasons, this analog system is not going to produce the same output every time. It's not going to produce the output we expect. So this is a really bad abstraction, right? If we had to deal with analog systems, it would be very hard to build large systems out of these components, which is why any time that you need to do some serious processing of information, you go digital. So what we want to do is go from this real world that has continuous quantities and noise and variations and imperfections and all sorts of things that are changing our signals over time to this ideal world where we have bits that are always 0 and 1 and never change, so that we can take some information, process it, manipulate it a billion times and get the same result every time. Now, this is what we're going to do over the next few slides, but always keep in mind that the world is ultimately not digital. So what we're going to be able to do with this, by encoding information digitally, is we're going to be able to tolerate some amount of noise. And so we're always going to be talking about noise margins. So things will work fine if you have noise that's less than 0.1 volts or 0.2 volts. But eventually, if you have enough noise or enough variations, things will break because the physical world is the physical world. Sometimes you get too much noise, you get too much variation, and the digital system stops working. So always keep that in mind. Okay, any questions so far? All right, so our strategy here is essentially to encode voltages digitally. We're going to choose a binary representation, so we're going to encode 2 symbols along our range of possible voltages. Let's say this goes from 0 volts to 5 volts or to whatever voltage your circuit has. And we're going to use the same convention for every component and wire in our digital system, right? So we're going to set a standard about signal levels so that different devices can talk to each other. So let's start with a very simple first attempt. If you have to choose ranges to encode 2 different symbols, we would choose, let's say, a threshold voltage, VTH, that is somewhere in the middle of this region, and then say, okay, every voltage that's smaller than this threshold voltage, it's a digital 0. Every voltage that's larger than this threshold voltage, it's a digital 1. Okay, that's simple. Unfortunately, this doesn't work. Can any of you guess why? Yes?
If it goes a little bit above and a little bit below, and a little bit above, maybe you want to stay at 0, but a lot more.
Exactly. So there are tiny variations, right, in our circuits. And so if you're just at the edge of what's a valid 0 and a valid 1, now a little bit of noise is going to push you over the edge and change a 0 to a 1 and a 1 to a 0, right? Let's just, see a more concrete example. Now you don't have to know what an operational amplifier is, but I'm just going to draw one. An operational amplifier is an amplifier with a very large gain. So it looks at the voltage difference between these 2 terminals and it amplifies it by a factor of 1,000,000. So if there's a tiny difference between these 2 terminals, a tiny positive difference, it will output VDD or 5 volts or whatever the supply voltage is. And if there is a tiny negative difference, it will output ground or the minimum voltage in the circuit. Right, so let's say that we want to just build some very, very simple digital device that just propagates whatever input signal you give it. Right, so this is the input voltage, and you are producing V out, which hopefully is a digital 1 if the input is a digital 1, a digital 0 if the output is a digital 0. And so we're going to choose two resistors that are the same, so that this is VTH is VDD over 2, right? So this voltage is a constant, is a divider, a voltage divider, right? Two resistors in series. This is the ratio of the values of the resistors, right? And so this, with two resistors that are equal on either end, is going to be VDD over 2, right? Except it's not, right? Except this resistor will be a little bit different, or this resistor will be a little bit different, or this resistor will be 0.1 degrees hotter, and that means its resistance is higher. And so this threshold is going to change. And so if you have values that are close to VDD over 2, or your threshold voltage, this is going to oscillate. So again, not a good standard. Okay, any questions? Good. Okay, so let's try something a little bit more complicated that tries to get rid of this problem. So instead of setting one threshold voltage, right, one single threshold, we can set two. A low threshold, which we're going to call VL, and a high threshold, which we're going to call V8. And then, essentially, we need some elbow room, so we're going to give ourselves that elbow room. We say, everything that's lower than this low threshold voltage, we'll interpret it as a valid digital 0. Everything that's above this high threshold voltage, we'll interpret as a valid digital 1. But how about things that are in the middle? What digital value does this range between VL and V8 represent? And so our answer is going to be, just don't tell me, just don't ask. You're not allowed to ask. It's undefined. I can give you anything. I might not even give you a valid digital value at the output. So essentially, by creating this band of undefined values, now we have this gap, right, that we can use to prevent these small manufacturing variations from flipping a 0 into a 1 and vice versa, right? So we're getting somewhere. We're pretty close, in fact, to deriving the right signal, or a good digital signal specification. But now there's one other issue that we still need to fix, and it's this one. In the end, what we want to do is take different digital devices, right? And these digital devices are going to have inputs and outputs, and we want to connect them in different ways, right? So we want to plug some digital output to some digital input. And if you just use the same signal levels for outputs and inputs, the following thing can happen, right? You have a valid 0, or this upstream digital device, producing a valid 0, but that's just slightly below the low threshold, right? Is this VL minus epsilon. And then there's a little bit of noise that happens in the transmission of this value to the input of this downstream digital device. So now this input is an invalid digital value. So again, we have the problem that a tiny amount of noise has flipped or has changed our valid 0 to an invalid value, or in general, our valid digital value to an invalid 1. So how can we fix this? Any guesses? Yeah.
Give it a random value as the
Give it a random.
Yeah, just give it 1 or 0. Yeah.
Well, no, the problem here is that we still want the downstream digital device to receive a 0, right? So, yes?
Do you, if it starts getting close to the boundary, somehow make it go back more away from the boundary?
That's getting closer, but it's not quite there, right? But you're on the right path. Yes?
Give the lows and the highs a range as well.
Sorry?
Give the lows and the highs a range as well.
So this doesn't have to do with the lowest value and the highest value. This actually has to do with the fact that both the output is producing something that is very close to the limit of what the input can accept, right? Yes?
How the output have some interval valid things and the input be shrink?
Exactly. So what we want is for the outputs to have a stricter specification than the inputs, right? So what's the problem here? The problem is that you have exactly the same voltage level, right, that being produced by the output than what the input can detect. If you say, the output has to be, every output has to produce low values that are at least, 0.1 or 0.2 volts lower than what the input can detect, now you have a little bit of margin, right? And so you can tolerate a little bit of noise, 0.1 or 0.2 volts, or whatever the difference between the output and the input range is, right? So basically, output voltages should use narrower ranges. You want a valid output 0 to be a lower voltage than what a valid input 0 is, and you want a valid output 1 to be a higher voltage than the lowest voltage an input will recognize as a valid 1. Is that clear? Essentially, we're creating now two different specifications for outputs and inputs. So let's formalize this. So this actually gives rise to the notion of noise margins. So what we're going to have is a specification that differs for inputs and outputs. An output, so we're going to define, instead of VL and VH, we're going to call these levels VOL and VOH, and we're going to say that a digital output must produce values that are at most VOL to be valid digital zeros, and at least VOH to be valid digital ones. So essentially we have this range of valid output representations, right? This is a valid 0, this is a valid 1, and this is an invalid output. And then for the inputs, we define two different thresholds that we're going to call VIL and VIH, right? So everything that is smaller than VIL, the input is going to accept as a valid digital 0. Everything that's larger than VIH, we're going to accept as a valid digital 1. And for the system to work, where do these thresholds need to be? Right? These thresholds need to be somewhere in the middle, right? You want VIL to be larger than VOL, and you want VIH to be lower or smaller than VIH. And essentially, this gives rise to this equation over here. So we have 4 different levels, right? And they have this relation always to be a valid digital specification. You want VOL being less than VIL, being less than VIH, being less than VOH. And ideally, you want these two margins, right? These two differences, VIL minus VOH, VOL, and VOH minus VIH, to be large, to be pretty large as you can make them. Why? Because these are the noise margins. Because that's how much noise you're going to be able to tolerate between an output and an input. Okay? Yes?
If you want these margins to be as large as possible, why not make VIL equal to VIH?
You could, and you can in practice make them pretty close. So yes. And the nice thing about this is that what I mentioned before about the output, about this threshold. Like, suppose that in the end you had a single threshold voltage and you had VIL equal to VIH. In practice, you're not going to be able to manufacture a device that has that exact threshold. But if you make it very small, you can maximize your noise margins. We'll see why you can't just get that to 0, because that eventually is unrealizable. So we'll see why in a second. Okay, any other questions? Yes?
What is the physical explanation for why VOH has to be higher than VIH?
The physical explanation is that you want to generate voltages that are higher at the outputs than what you can accept as a valid voltage at the inputs. That way, if you get some voltage drop on the way between an output from an output to an input, the input still gets the correct value. That's the physical explanation. It's all about tolerating noise. Yes?
If our input is between VOL and VIL, for instance, how do we decrease that voltage value to get below VOL for the output?
That's a great question. So this is going to require something from these devices, right? And we'll see exactly what that is in a second. And so just to summarize things, a digital device must take marginal inputs that are almost undefined, right, almost not valid, and then produce unquestionable outputs that are within this narrower range of 0 to VOL and VOH to VDD. Right? So you're taking inputs that are almost bad and then turning them into good outputs. And that is going to imply something or require something of the system. We'll see in a second what that is. So, we can see this as digital systems being restorative. And so that means that they're restoring the signal over time. So in an analog system, you can have noise being injected at different points. Right? And so the noise is going to accumulate, and the analog system is going to, then produce a function that depends on its input voltage, and that incorporates some noise term, and then some other amount of noise is going to accumulate here, and then, this second analog component will process it, and we'll get, more noise in the output. This is why, if you want to, do 1 billion instructions or perform 1 billion instructions on some value and it's encoded as an analog value, you're going to have a bad time, because in the end that is going to be garbage. By contrast, digital systems cancel noise at its stage, right? So even if you have noise being injected between inputs and outputs, this F here, this digital F, is going to produce a value at the output that is the same, or at least by the specification within the same range as the value that you would have if you didn't have the noise, right? And so even though you're adding noise, you still get noiseless values at the outputs. And that is why we can take a value and process it a lot of times and still get reliable results. So now, this leads me to, what does this demand of these digital systems? Well, it demands them to fight noise, to cancel noise, and that you can only do with active components. Essentially components that amplify, components that take small voltage differences and produce high voltage differences. And these are called active components because they're components that inject energy into the system. They're connected to the supply voltage, and they're injecting energy in certain cases. And we'll see later in the course how transistors work and how gates are actually implemented and how these devices work in detail. But just at a high level, we're going to see why you need these active devices by looking at what we call the voltage transfer characteristic, or VTC. So to show what the VTC is, let me first describe perhaps the simplest digital device, which we call a buffer. So a buffer, which is represented with this triangle over here, just copies its input value to its output. And it copies a digital input to a digital output. So if you give it a valid 0 as an input, it will put a valid 0 at the output. If you give it a valid 1 at the input, it will put a valid 1 at the output. Now, what the voltage transfer characteristic shows is, for each input voltage that you put into this device, or into any digital device, how does the output voltage change? What output voltage do we get? And to produce this voltage transfer characteristic, this VTC, we were interested in static behavior. That means that there's going to be some transition, right? But we are not interested in what happens on the transition. We just want to see what the final voltage value at the output is, given one particular input value, right? So if we draw our digital thresholds, or our signal thresholds here, right? So we have VOH, VOL at the output, and VIL and VIH at the input. you can see graphically what this means, what having a specification means in terms of what the VTC of a device must be. Specifically, you cannot have a VTC that has, that has any point in any of these shaded regions. Why? Well, because each of these shaded regions is showing a valid input, right, and an invalid output. So you must have a voltage transfer characteristic that stays in the white regions, but not in the shaded ones, right? So now if you go and measure all the different points, let's say you take all these different measures, you'll get something like this typically, right, where you get this nonlinear function. You get, some low gain at the beginning, and then eventually you get this high gain in the middle, and then it stabilizes. And the point is that, whatever, given this signal specification, you cannot get into these shaded regions here, right? Okay, so this has some implications on what we demand from the device, and specifically, note that the height of this rectangle, this white rectangle in the middle, is by force larger than its width, right? And that's because VIH minus VIL, right, that is the width, must be smaller than VOH minus VOL. So if we want to have a device that traverses this way, right, that needs to stay in the white regions, this implies that at some point, right, in this region, the gain of the device needs to be larger than 1. And by gain, I mean the derivative of the output voltage with respect to the input voltage, right? Is the gain of a device is essentially if you apply a small increase to the input voltage, right, how much does the output voltage grow? And so in this case, you can see that the gain is pretty high here, right? Now, if you had resistors, capacitors, inductors, right, everything you saw in 802, you couldn't get a gain larger than 1, right? You could get, for example, with a resistor, you'll get something like this, right? But you can't get a gain that's larger than 1. And that's essentially what's forcing these digital devices to have active components. And today, these active components are all transistors, and we'll see transistors in a couple of lectures. Okay, the other thing that's important to remember is that we actually don't ask anything of the device in this middle region, right? So on this region, right, you must have a valid digital value. On this region, you must have a valid digital value, but the VTC can do whatever in the middle, right? So as the device transitions from 0 to 1 or from 1 to 0, it could go through all sorts of signal levels. It can go up, down. As long as it doesn't get into the forbidden zones, we're good. It's a valid digital device. Okay, any questions? Yes?
Why don't we forbid the region above the left rectangle and the region below the right rectangle?
That's fine. That's a great question. Why don't we forbid it? Because when you're transitioning between a low digital value and a high digital value, you can have valid or invalid outputs, and it doesn't really matter. We should build systems that are resilient to having high and low voltages in the middle. And we'll see in a second that we actually don't care. So we can actually build systems that absolutely do not mind what values you have in the middle. Okay, so this brings me to a brief overview of digital circuits, right? So we've looked at the input and output specifications, right? We've looked at what goes on in the middle of these devices, but what's inside the box, right? So inside the box, you'll find one of two broad classes of circuits. We have the type of circuits that we'll study first is what we call combinational circuits. The circuits do not have memory. And so they're called combinational because each output is defined or has a constant value given a particular combination of the inputs. That is, the output is a function of the inputs, of the input values, exclusively. Right? There's nothing else inside this box that's essentially changing the value or affecting the output. And there are many examples that we will see over the next few lectures. Some very simple ones are the inverter, which is a device that essentially turns a 0 into a 1 and a 1 into a 0. And we can also have devices with multiple inputs. So for example, this is an AND gate, which implements the logic AND function we've already seen. So essentially the output is 1 if both inputs are 1, and otherwise it is 0. Okay, so in the next few lectures we'll actually do a deep dive into combinational circuits. But we'll build towards a more general class of circuits that we call sequential circuits. And the difference between combinational and sequential circuits is that sequential circuits have memory. We call this state. Sequential circuits have some bits inside this box. And these bits are, in general, affecting the particular values of the outputs. And so its output is no longer a function of only the inputs, only the current inputs. But it is a function of the current state of this circuit and the current inputs. In other words, it's a function of the sequence of inputs that we've given it in the past as well. And that's why these devices are called sequential, because the output is a function not only of the current input, but also of all the previous inputs we've given them. Okay, so let's actually jump into a brief introduction of combinational circuits. Combinational circuits are the most basic, fundamental building block of digital logic. And the reason we like them so much is they're super easy to compose, right? We've been working on all this, getting all these signal levels right, and now I'm going to show you, why it's so great to have, a robust signal specification, because we can get devices that compose very easily. So a combinational device needs to satisfy this, what we call the combinational contract or the static discipline. It needs to have one or more digital inputs, one or more digital outputs. Essentially, the inputs and outputs need to obey the convention, the signal levels that we've discussed before. And then it needs to have two other things. A functional specification that precisely tells you how each output depends on the values of the inputs. That is, what is the value of the output for every combination of the inputs. And then a timing specification that at least consists of what we call a propagation delay. And this is basically, the propagation delay is a bound or an upper bound on the time that you take from having valid inputs to producing a valid and stable digital output. Why do we want to have a bound on that? Well, because we want these circuits to eventually produce an answer, right? And so you'll see the role of this propagation delay in a bit. But essentially, functions, outputs are functions of only the inputs, right? And after some time elapses, we'll get a valid digital output, right? So in this case, this is the functional description of this particular circuit. Output a 1 if at least 2 out of the 3 inputs are 1, otherwise output a 0. And then this device says that it will generate an output in no more than 2 minutes after seeing valid inputs. Now, 2 minutes is quite a bit of time. This is a majority function. It's if 2 out of the 3 inputs are 1, you'll get a 1 at the output. And we'll see in a couple of lectures that you can compute that in about 50 picoseconds. So 50 picoseconds is a bit less than 2 minutes. Okay, and as I mentioned, the combination of these 4 things is called the static discipline. Okay, so the key reason we care about combinational devices is that, as I mentioned, they're very easy to compose. And so a set of elements, interconnected elements, is a combinational device if you have these 3 properties. And these properties are sufficient, but in general not necessary conditions. The first one is each certain element is combinational. Then you have every input connected to exactly one output or a constant value. This could be a 0 or a 1, something that's providing 0 VDD voltage. And then the circuit contains no directed cycles. Okay, So rather than going in detail into what can go wrong if you don't obey these properties, which we'll do in a second, let's first go through an example. So assume that you have this circuit over here, right, that has A, B, and C, and I tell you that they're all combinational devices. Can you tell me whether the following circuit is a combinational device? Well, to do this, we can just go through the different elements of the static discipline and see if that's the case, right? So first question, does it have digital inputs? I see many people nodding, so okay, what are these inputs? This input, this input, this input, great. Now, these are inputs to these two devices which are combinational, so they have digital inputs, so yes, all the inputs of this circuit are digital. Does it have digital outputs? Same reason, right? The output, the only output of this circuit is the output of C, which is a combinational device, therefore, yes, it has digital outputs. How about, can you derive a functional description? Can you tell me, right, if I give you the functional descriptions of circuits A, B, and C, what the functional description of the output is? This is a little bit more complicated, right? So let's go through it. So if we name these inputs to X, Y, and Z, and we name the output to, let's say, W, right? Let's start with A. What value do you have here? We'll have some function fa that is function of X and Y, right? What value do you have here? If this circuit B implements function fb, well, we'll have fb of what's this input? Fa of xy, comma c. Right? What is W? Well, it's fc of fa xy, comma, and this whole thing over here, right? fb fa x y z, right? So if I give you the functions of each of these three circuits, you can compute the function of the overall thing. What about timing? So can you derive a propagation delay? Now remember, the propagation delay of each of these components, right? Let's say they're TPD A, TPD B, TPD C, are I give you the propagation delays of each of these, which are an upper bound on the delay from valid inputs to valid outputs. How would you compute the propagation delay of the whole thing? Yes?
Sum the delays across each element.
Exactly. So in this case, you have to find the longest path, which we call the critical path to the circuit, which is from A to B to C. And so in this case, it's just the sum of the propagation delays. Okay, so what I want to do in the remaining 2 minutes of this lecture is, rather than finishing with the couple of slides that come after this one, is go back and talk a little bit about what happens when these conditions are not met. So every circuit element being combinational is obvious. We want to build combinational circuits out of other combinational circuits. What happens if every input is not connected to exactly one output, right? So if we leave an input floating, what happens? If I, just didn't have this. Could you tell me the function that this would compute? I mean, who knows what voltage is in here, right? Essentially, there's nothing driving this, and so in general, it's going to oscillate. We don't know what value it's going to have. What happens if we connect multiple outputs to the same input? What could possibly go wrong? So if the outputs don't produce the same value, they'll fight with each other, right? In general, you can burn your circuit. So we drive every input with a single output. Finally, we have this condition that the circuit cannot have directed cycles. Let me just show you why. So we already have all the tools we need to produce really bad behavior. Okay? So suppose that I have this circuit. It has a loop, right? Initially, I have a 0 here and a 0 here. So this is a 0. This is a 1. This is a 1. Fine. Even if you have a 0 and a 1, you have a 0 at the output. This is stable, right? So you have a 0 at the input and a 1 at the output. Now suppose that I set this to a 1. What's going to happen? This turns into a 1. This turns into a 0. This turns into a 0. This turns into a 0. This turns into a 1. This turns into a 1. You can see what's going on, right? Our output is going to oscillate, and we don't have a TPD for that. And so in general, we're going to insist that we do not have cycles in our combinational devices. So in the next lecture, we'll figure out how to precisely define the specification for these different combinational devices. All right, that's it for today. Thank you.